Hello, we're going to talk about integration. So what we're going to do is we're going to start with exploring the ideas on evaluation of integrals, which means how can we define the area underneath the graph of a function. And then in the next video, we're going to talk about, in fact, the actual definition of integral. Okay, so here is one thing that we're going to keep in mind throughout this chapter. All of our intervals are from A to B and they are all of positive length, so we don't do interval from A to A itself because that would be just a little bit inconvenient. And all of our functions are bounded. When we are dealing with unbounded functions, integrals would be a bit more complicated. Okay, so how do we define integral? So in order to define integral, and this is something you have seen, the idea is something you have seen in single variable calculus. If you want to define integral of a function, what we do is we take the interval from A to B, we divide it into small pieces, and then for each piece we approximate the area, and these areas that you find, if they in some ways, if they approach a certain number, that number is called integral. But since there are many different ways of partitioning the interval AB, we can say that we cannot just take a sequence. There are many different kinds of partitions. There's really no sequence. What we can do is this. What we are going to do is we're going to take the largest area that we can fit into this. So if you look at this, the largest rectangle fitting into the first region is this rectangle. The largest rectangle that we can fit into this one is this rectangle. The largest one into this one is this rectangle. Then this one, and then finally this one. This sum is definitely going to be less than or equal to the integral if we can define some idea of integral. And on the other hand, if we define if we look at these areas, area of this one plus area of this one plus area of this one plus area of this and plus area of that, this would be an upper bound for the integral. And what we are going to do is we're going to use those lower bounds, those blue regions, and we used those to get what we call a lower integral. We use those green regions which are above upper bounds for the area, and we call those upper integral. We define upper integral to be the infimum of those. And then if this upper integral is equal to the lower integral, then we say the function is in fact integrable. Or in fact, we can make sense of the area underneath the graph. Okay, so let's get started with some notations. So it's quite notational. So I'm going to stick to this notation and I'm going to put out all of that in definition 7.1. Given an interval a to b, let x naught equals a x1. So the initial point is x naught, next one is x1, then x2, and so on. The last one is xn. So this is a partition. This is called a partition. x0 all the way to xn is called a partition of AB, interval AB. In every partition, we always list the elements in increasing order. The gap of a partition is defined to be the largest of xi minus xi minus 1. So in this, in the partition on the right, this is the gap of the partition. At least it looks like it is the gap of the partition. It's the largest of these length. And what I would like to do eventually is to make sure that this gap is very small. Or in fact, I would like to allow the gap to go to 0. Okay. So what are we going to do with a partition? What we are going to do is we're going to look at the minimum of the function, or I guess not minimum because it may not have a minimum, but it has an infimum. Because it's a bounded function, we have infimum. Infimum of the function over each of these intervals is called lowercase mi, and supremum is called capital Mi. So mi would be these blue lines, and capital Mi's would be those green ones. Now, we will take the areas of those blue regions. So each one of them would be lowercase mi times the length of the interval. So lowercase mi times xi minus 1. And then capital Mi times xi minus 1. So those are the upper sums. Those are called upper sums. So again, we define and denote the lower sum as sum of mi times xi minus 1. And we define the upper sum as sum of mi times xi minus 1. The only difference is one of them is lowercase mi, which is the infimum, and the other one is capital Mi, which is the supremum. And this notation is what I will be using throughout this chapter. So I won't, every time I won't really introduce these these variables. So the above notation will be used throughout this chapter. So note that infimum is always less than or equal to supremum. Therefore, the lower sum is always less than or equal to upper sum. So if you take a partition, the lower sum of the partition is always less than or equal to the upper sum of the same partition. Okay, so let's just start with an example to understand the idea of this lower sum and upper sum. Define a function f from ab to r by f of x equals 1 if x is rational and 0 if x is irrational. Determine the upper sum and lower sum of f for each partition. So let's say that P, the partition, is x0, x1 all the way to xn. So again, I'm gonna let this be the partition. And I will have to find, in order to find the upper sum, I will have to find the supremum over each interval. In order to find the lower sum, I will have to find the infimum over each interval. So, what is the supremum of this function over each interval? In every interval, there is a rational number and there's an irrational number. So, and that's because of the fact that Q and Q complement are dense. In each xi minus 1 xi, there is a rational and an irrational number. Thus, lowercase would be 0 and uppercase mi would be 1. So this means if I look at the lower sum, I would get the sum 0 times xi minus 1. So all of these terms are 0. And upper sum would be, upper sum of fp would be the sum I equals 1 to n. Capital Mi is 1 times xi minus 1. This is a telescoping sum. So it's a telescoping sum that we did, in fact, like the very first day of class. And this is b minus a, or xn minus x0, which is b minus a. Since it is a telescoping sum. So to summarize, we got that lower sum is 0 and upper sum is b minus a. And that's the end of the solution for this one. So going back, they asked us to find the upper sum and lower sum for each partition. In fact, lower sum and upper sum do not depend on our partition in this case. Whatever partition that you take, the lower sum is always 0, the upper sum is always b minus a. Let's see why that makes sense. If you look at the function is 0 a bunch of places and 1 a bunch of places. And the fact about these bunch of places is that they are dense. So if you look at this interval, there is no way you can fit an area underneath the graph of this, because even if you start with like a tiny rectangle, there is some point inside this rectangle, so that would not be completely underneath the graph of the function. So that means the only thing that you can fit underneath it is 0. The only area that you can fit underneath is the segment from A to B. And the smallest rectangle that contains the graph of the function is this rectangle. And the height is here is 1. And its area is of course b minus a, which is why the upper sum is b minus a and the lower sum is 0. Okay, so now one thing that intuitively makes sense is that if I take two partitions, I'm gonna draw this. So let's say I'm dealing with this partition. This is my partition P, x0, x1, and x2. So this is partition P. So P is x0, x1, and x2. If I look at the lower sum, it would be this. This would be the lower sum. Now, if I take this partition and turn it into add some more points. Let's say I add one more point here. What am I going to end up getting? I get this one as the lower, so the other side remains the same. So the lower sum becomes larger. So the partition, I'm going to call this one perhaps like Z. So let's say Q is x0, Z, x1, and x2. If I add one more point, or even more than one more point, the lower sum becomes larger because we are adding this amount. So the lower sum becomes larger. Now if you look at the upper sums and compare them, upper sum for the first one is this. For the second one, up to here is the same. You're gonna lose this amount. So upper sum, when you add more points to the partition, upper sum becomes smaller, but lower sum becomes larger. And it makes sense. If you're adding more points, you are gonna get closer and closer to the curve, which means your lower sum becomes smaller and your upper sum becomes, lower sum becomes larger and the upper sum becomes smaller. Okay, so now let's formally state that, and we're going to prove that. Suppose P and Q are two partitions of AB. We say Q is a refinement of P if P is inside Q. It means all of the points of P are in Q and perhaps some more additional points. This lemma tells us, this is a very important lemma. It's called the refinement lemma. It says, suppose you have a bounded function f and P and P star are partitions of AB for which P star is a refinement of P. So it means P is inside P star. Then lower sum of P relative to P is less than or equal to lower sum relative to P star, less than or equal to the lower sum relative to P, upper sum relative to P star. This one we have proved before. we know that lower sum is always less than or equal to upper sum for the same partition. And that's less than or equal to the upper sum of f with respect to p. Okay, so we are going to prove one of these inequalities. We're going to prove this one. And then the other one would be similar. So I'm going to prove this one. This would be quite similar. We have proved this one before. Okay. So we have proved the lower sum is less than or equal to the upper sum. So we're gonna ignore that one. Okay, so let's first assume, so what I'm going to do is this. I'm going to show that if I take the lower sum and if I add if I add 1 point to the partition, then the lower sum becomes larger. And therefore, if you keep adding points to the partition, the lower sum becomes larger and larger. So first, assume P star contains precisely 1 additional points compared to P. So you have P and you're adding 1 additional point to that. So let's just say that additional point is Z. So let P is x0, x1, and then xn, and let P star be x0. Let's say it's xi minus 1, then Z, that's the extra point, then xi all the way to xn. So i.e. P star is P with the additional point of Z. Now, if you write down the lower sum for f with respect to P, you will get the sum mi and then times xi minus 1, where mi is infimum of f of x, where x is from xi minus 1 to xi. And this is from 1 to n. If you look at the lower sum of f with respect to P star, you will get, first you will get, here it would be basically the same thing. You will get mi, I equals 1 to I minus 1, xi minus xi minus 1. That's the exact same thing. Or I should call it perhaps, okay, maybe I will change this one to k, just to make it more clear, because I don't want to use the same thing, same letter. Okay, so I have x0 to xk minus 1, then z, then xk. So the first portion from 1 to k minus 1 would be the same, plus, then I have to take the infimum over this interval and multiply that by z minus xk minus 1. Then I have to take the infimum over, so this would be a, the infimum over this one, I'm going to call that b. I will write down what b and a are. xk minus z. And then I will have to take the rest of it. mi xi minus xi minus 1, I equals, so the first one would be k plus 1, the last one would be n. I'm basically skipping one term from the partition from the one for partition P, and I'm adding 2 terms, where a is the infimum of f of x, where x is in the interval from xk minus 1 to z, and b is the infimum of f of x, where x is from z to x k. Okay, now if I subtract these two, if I do the lower sum for f with respect to p star and subtract the lower sum for f with respect to p, I will get three terms. This term and this term do not exist in the other one. And the term for k does not exist in the bottom one. So this would be a times z minus xk minus 1 plus b times xk minus z. So these are the two terms here. Minus mk times xk minus xk minus 1. Okay, now if you look at this quantity, I need to show this quantity is in fact non-negative, and that proves the inequality that we want. Okay, A is the infimum of this interval, this set, and I know mk, so if x is in the interval xk minus 1 to z, then x would be in the interval xk minus 1 to xk, which means f of x is greater than or equal to mk, because mk is the infimum of f of x inside this interval. So that means mk is a lower bound for the set f of x, where x is in the interval xk minus 1 to z. Because what we showed is that f of x is greater than or equal to mk for every x inside this interval. So that means mk is a lower bound for that. So that means mk must be greater than or equal to the infimum of this set. But infimum of that set is a. Infimum of this set is a. mk is a lower bound. And I'm sorry, the other way around. mk is a lower bound. A is this largest lower bound. So a is greater than or equal to mk. Infimum is the largest lower bound. mk is a lower bound, and a is the largest lower bound. Similarly, b is also greater than or equal to mk. Now watch what happens when you write down what we found up there. Lower sum for f with respect to p star minus lower sum for f with respect to p is equal to a times, if you go back and see what we had, z minus xk minus 1 plus b times xk minus z minus mk times xk minus xk minus 1. Now, we know this is positive, and we know this is positive. So we are going to multiply this inequality by z minus xk minus 1 and multiply the second inequality by xk minus z. So this is what we get. And this is clearly 0. Everything cancels. So therefore, the lower sum for p star is greater than or equal to the lower sum for p. And that proves one of the inequalities. As we discussed, the second inequality was proved before. This was proved before. The one on the right has a very similar proof. So similarly, we may prove the other one. upper sum for P star does not exceed upper sum for P. So if you look at what we did here, is what we showed here is that if you refine your partition, your lower sum becomes larger, your upper sum becomes smaller, or it could stay the same, but it definitely doesn't, lower sum doesn't decrease, upper sum doesn't increase. Okay, as a consequence of that, if you take a any partition, any two partitions, lower sum for for one partition is always less than or equal to the upper sum for the other partition. And the proof isn't that difficult if we consider if we use the refinement lemma. So take this partition P union with K. This is a refinement of both P and Q. Thus, by the refinement lemma, lower sum of F P is less than or equal to lower sum of F P union Q. And upper sum of F P union Q, when I refine it, upper sum becomes smaller, or at least doesn't get larger. But we know that this one, lower sum, is always less than or equal to upper sum, since lower sum of F with respect to the union of P and Q is less than or equal to the upper sum of F with respect to P union Q. We have that lower sum of F with respect to P is less than upper sum of F with respect to Q. And that's exactly what we wanted to show. So lower sum of every partition with respect to every partition is less than or equal to the upper sum with respect to every other partition. So that means if I take all of the lower sums, they are bounded above. The above corollary shows that the set of lower sums is bounded above, because just take any partition that you want. So the lower sums are bounded above by the upper sum of any partition. So, and the upper sums are bounded below by any of the lower sums. This motivates the following definition. Okay, so the lower integral of F is defined as the supremum of all of the lower sums. So we take all of the lower sums and we take the supremum of those. That's called the lower integral. Similarly, the upper integral is defined as the infimum of all of the upper sums. So infimum of all of the upper sums is called the upper integral. Okay, so let's do an example on this one. So again, this follows what we just talked about at the beginning. We take all of the lower sums, which means all of the areas that fit underneath the graph of the function, and then we take the supremum of all of those. That would give us the largest area that fits inside the graph. And then that's called the lower integral. And then we do the exact same thing on the opposite side. We look at all of those areas that cover the whole region, and then we take the infimum of those. That would be called the upper integral. Okay, for example, if you look at this function, we want to find the lower and upper integral of this function. So this is the same function that we saw in example 7.1. By example 7.1, lower integral is 0 and upper integral is b minus a for every partition. And I don't even need to use two different letters. So thus the upper integral of f becomes, I will have to take the infimum of all of these lower sums, but there's only one number in there, so that's just b minus a. And lower integral is the supremum of, there's only one number in there, so that's just 0. So thus lower integral is 0 and upper integral is just b minus a. And that's the end of the solution here. Okay. And it makes sense based on what we discussed before. It makes sense. Look at this graph. So the smallest rectangle fitting underneath the graph of this function is just nothing, a segment. The largest rectangle fitting underneath the graph of this function is just a segment. So the area is 0. The smallest rectangle covering the whole region is rectangle with base b minus a and height 1. Okay. Great. So now we are going to discuss a theorem. For every bounded function f, we have that the lower integral is always less than or equal to the upper integral. It makes sense that the lower integral must be less than or equal to upper integral. But how do we prove this? So we know that by, I guess I called it corollary 7.1. So by corollary 7.1, lower sum is always less than or equal to the upper sum for every two partitions of AB. Now, fix your partition P. So fixing P, note that this lower sum of FP is a lower bound for this set, for the set of all upper sums, such that Q is a partition. Lower sum is a lower bound for the set of all of those upper sums. Now, by definition of upper integral is the supremum of this set. I'm sorry, it's the infimum of this set. Upper integral is the infimum of this set. Lower sum is a lower bound. So which one is larger? Lower sum or infimum? Infimum is larger. So by definition of this, lower sum of f is less than or equal to the infimum, because lower sum is a lower bound and upper integral is the infimum. Infimum is always the largest lower bound. Okay, this holds for every partition. So what does that mean? Therefore, upper integral is an upper bound for this set, for the set of all lower sums. Lower sum of f relative to P, where P is a partition. So this is an upper bound. The upper integral is an upper bound for this set. So by definition of lower integral is the supremum of this set. This one is one upper bound. This is the supremum. So supremum must be less than or equal to that. So this is an upper bound. This is the least upper bound. So by definition, lower integral of f must be, which is the supremum, must be less than or equal to the upper integral, which is 1 upper bound. And that's exactly what we wanted to prove. Okay, so again, going back and seeing what we did, the lower integral is always less than or equal to the upper integral. And that makes sense because the lower integral was trying to underestimate the area, and the upper integral was an attempt to overestimate the area. And in fact, that is the same. That is in fact correct. Okay, so let's do an example. And that's the last thing we're going to do today. Let m less than or equal to m, lowercase m less than or equal to capital M be two real numbers. Prove that for every a less than b, there is a function for which the lower integral is lowercase m and upper integral is capital M. So this is interesting. In other words, it tells you that the lower integral and upper integral could be any number that you want, as long as you make sure that the lower integral is less than or equal to upper integral. So there is no other relation between these two. So let's see what we want to do. What we want is, we want the area to be capital M for the upper integral, and this goes from A to B. And if you want the area to be capital M, this would have to be M over B minus A. And then it would have to be lowercase m, so it would have to be M over B minus A. So what we're going to do is we're going to make sure that we have this value in every interval, the value of both values of capital M over B minus A and lowercase m over B minus A. How can we do that? Using a similar strategy. Choosing a set that is dense and its complement is also dense. So define, this would be something very similar to the Dirichlet function. Define f from AB to R by, so f of x would be equal to m over B minus A if x is rational, and lowercase over B minus A if x is irrational. So similar to the example that we did, example, I believe it was 7.1. Go back and look at the example that we did. Yes, 7.1. 7.1. Lower sum would be M over B minus A. So this would be all of the infimums and then times B minus A, which is M. And upper sum is going to be capital M over B minus A times B minus A. It's the exact same process for every partition. Now, by definition, lower integral of f is going to be the supremum of all of the lower sums of m, which is m. And upper integral of f is the infimum of all of those upper sums, and that is capital M. And that's exactly what we wanted to prove. So in other words, lower integral and upper integral have really no other relation except that lower integral is always smaller than or equal to the upper integral. Okay, so this brings me to the end of the discussion for today. If you would like to continue with this topic of advanced calculus, feel free to subscribe, and I will see you in the next video.